the sequel.
Literally. The sequel.
No, limits the sequel.
That's scary.
Moron.
All right. Finding a limit. So if we had the limit as x approaches 1 of x cubed minus 1 over x minus 1, first thing I always look and say, can I plug in whatever x is going to, and it exists. Well, the problem is if I plug in 1 on the bottom, that gives me 0, and the denominator undefined, so I can't do that yet. So what I want to do is I want to see if I can factor the top and see if something will cancel, or try that. So does anybody know what the top is?
Like a
It's
Yeah,
a difference
like,
of cubes.
Difference of cubes. Does anybody remember what it factors into?
literally no.
Three
Um,
like 3x.
Yeah, I couldn't tell you.
I didn't know there was a difference of cubes.
If I said soap, does that ring a bell?
Absolutely
So,
not.
Oh, wait.
Subtraction,
So
opposite.
Wait.
That
I think I'm thinking foil, but in different letters.
What is-
Like I know what
I
it
know,
is, but I
it's-
don't know what they stand for.
All right, same sign, x minus 1
Same. Oh, okay.
times x squared, opposite sign, so plus, and then it's like each thing multiplied by each other, but since it's just 1, it's just x. And then always positive, plus 1, which would be squared,
Oh.
over x minus 1.
Oh.
So then these things nicely cancel. And so we have the limit as x approaches 1 of x squared plus x plus 1. So that would just be 1 plus 1 plus 1, which is going to be equal to 3.
Can you explain the
Yeah.
middle in the x squared plus x? Can you explain why that's x?
Yeah, so if we had, let me just do it this way, it'll be easier. So if we had a cubed minus b cubed, because you'll agree that 1 could also be 1 cubed,
Yeah.
right? Okay. So that's where that's coming from. So it's a minus b, so same sign. Then it's a squared, opposite sign, so in this case it'll be plus ab, and then always positive plus
Okay.
b squared would be the generic. And if it was a cubed plus b cubed, then it would just follow the SOAP formula, but it follows the same.
So what does
Same.
soap mean? Like,
Same sign, opposite sign, always positive.
I do remember this.
It's just been a while because it doesn't get used very often.
Yeah.
All right. Using limit properties. So this is going to be several problems involving these properties here that are pretty self-explanatory, but, you know, nonetheless, we wrote them. So we are going to use the fact that, this is what I wrote yesterday, the limit as x approaches 0 of sine of x over x is equal to 1. So that's going to be helpful. That's just a limit you just need to memorize, along with the properties to solve the following. So the first one, so we're going to do 3, but the first one is the limit as x approaches 0 of x plus the sine of x over x. So would you agree that if I have something like the x plus the sine of x over x, that I can split it and write x over x plus sine of x over x?
Yeah.
Okay. So I'm going to have the limit as x approaches 0 of x over x plus the sine of x over x. Then by our sum rule, we can split this into 2 separate limits. So the limit as x approaches 0 of x over x plus the limit as x approaches 0 of sine of x over x is equal to, now x over x is what? 1, so that's going to become 1. So I have 1 plus the limit as x approaches 0 of sine of x over x is 1.
Yeah.
What? Because you're substituting the.
For this.
Oh.
So then that's equal to 2. So that's what that limit's equal to. So again, if whatever we had been plugging in had made it so that our limit did not have a 0 on the bottom to begin with, we would have just plugged it straight in. But more often than not, the whole point of taking a limit is because you can't do that. So you're going to have to manipulate it around using the rules to be able to solve it. The next one, the limit as x approaches 0 of 1 minus cosine squared of x over x squared. What do you see about this one?
Isn't that like an identity or like a property or something?
Yep. Which one is it? Or what's it equal to?
That's like a diagram.
Sine squared.
Yep, it's sine squared. So sine squared plus cosine squared is equal to 1. So having that gives you sine squared of x over x squared. But that's still a problem because it's still going to give me a 0 on the bottom. So I'm going to split this into the limit as x approaches 0 of sine of x over x times the sine of x over x. Now, by the product rule, or whatever we called it, is that what we called it? Yeah, it is. I can split them into two separate limits. So the limit as x approaches 0 of sine of x over x. Why did I have over s up there? Okay. Times the limit as x approaches 0 of the sine of x over x. So what is this limit?
It's what? No.
What's sine x over x? 1 times 1 equals 1. That's why I say that knowing that one limit in particular is very important.
Like I knew it was 1, but it still said 0. I'm a little tired.
All right, the next one, the limit as x approaches 0 of the cube root of sine of x over the cube root of x. So these have the same root, so I can actually write this all under one radical. So the limit as x approaches 0 of the cube root of the sine of x over x. Now, we had a rule yesterday that said that we can put the limit inside. If that happens, it was the root rule. So the cube root of the limit as x approaches 0 of the sine of x over x. So what is this limit? 1. So the cube root of 1 is just 1.
And you know that because of the rules?
That I was allowed to do this? Yeah.
Okay.
There's a, whatever I said, it was a radical rule or root rule. That's really hard to say.
Yeah.
I thought you said fruit roll.
He guessed it's a fruit roll.
I want a fruit roll up.
I was like somewhat confused.
All right, next example, finding limits by substitution. So we're going to have two of these. So the first one, the limit as x approaches 0 of e to the x minus the tangent of x. Whoops, not tangent raised to the x. Tangent of x over cosine squared of x. So now it may not be super recognizable, but these functions are continuous. So I am going to split this. Okay, so I have the limit of a fraction, so I can write the limit of the top and over the limit of the bottom. So the limit as x approaches 0 of e to the x minus tangent of x over the limit as x approaches 0 of cosine squared of x. So that's the quotient rule. Then by the difference rule, I can write the limit twice up top here. So this is the limit as x approaches 0 of e to the x minus the limit as x approaches 0 of tangent of x over the limit as x approaches 0 of cosine squared of x. And so then now I can just plug in 0 for x in each of these. So it will be e to the 0 minus the tangent of 0 over cosine squared of 0. Now what's e to the 0? 1. What's tangent of 0?
0.
0. And what's cosine of 0 squared?
0. Oh, it's undefined.
Oh wait, cosine of 0 is not 0. X value. Yep, 1. So 1 over 1 is just 1. Now, some people prefer to write this cosine squared of x as the limit as x approaches 0 of the cosine of x and then square the whole thing just so that they see it better. So that's fine either way, technically, that you want to do it. It's one of the rules, the power rule or whatever it is that allows you to do that. All right, next one. The limit as n approaches 16 of the square root of n over log base 2 of n. That's something we haven't seen in a while.
Log.
Yeah. All right, so this would be the limit as n approaches 16 of, and I can split it into 2. So the square root of n over the limit as n approaches 16 of log base 2 of n. Now, is there going to be any problem for me plugging in 16 to the bottom? Is there any risk of that being 0? No, so I'm going to go ahead and plug it in. So the square root of 16 over log base 2 of 16. Square root of 16 is 4. Log base 2 of 16 is log base 2 of 16 is equal to x. So 2 raised to what power gives you 16?
3. No,
That's 8. 4. So that's the work for that. So 4 over 4 is 1.
It's always 1.
You teach right now?
Yep.
I bet.
I won't be done till the end of class.
You said what?
I won't be done till the end.
You won't be done soon. I just see you in fourth period.
Okay. All right. Any questions about those two? All right. Next one. Finding left and right hand limits. So we're going to find the limit as x approaches 2 from the left of f of x and the limit as x approaches 2 from the right of f of x, where f of x is equal to, it's piecewise function, negative x squared plus 4x minus 1 if x is less than or equal to 2, and 2x minus 3 if x is greater than 2.
And they give you all of that?
Yeah, that would all be given to you.
What is if the top one, if x is less than or equal to?
Yeah. Trying to smush it in there. Now, if you were to graph this function, okay, you would be able to see that the limit is going to exist. Okay, each limit individually is going to exist, but they're not going to be equal. Okay, so, but we can do that algebraically as well. So the limit as x approaches 2 from the left of f of x is equal to the limit as x approaches 2 from the left of negative x squared plus 4x minus 1. Now, essentially, I'm just plugging in 2 to see if it works. I'll show you in a minute what's really happening with a different function. That'll make it easier to see what's happening if you look at it from the left and from the right, and why it can sometimes, or why it won't be equal. But I'm just going to plug in 2. A lot of times if it's from the left, I'll plug in like 1.999999, like mentally, and see what's happening. But just plugging in 2 is fine for the sake of this problem. So negative 2 squared plus 4 times 2 minus 1. Negative 4 plus 8 minus 1 is 3. So that's the limit from the left. The limit from the right, again, a lot of times I'll think about this as like 2.00001, something like that. So it's just a little bit over, but for the sake of this problem, we can just plug in 2 and it will show us what we're looking for. So the limit as x approaches 2 from the right of 2x minus 3. Plug in 2. 2 times 2 minus 3 is just 1. So the limit exists, but it's not equal. So the entire limit technically would not exist. But each individual limit does exist. If that makes sense. All right, next one. Finding a limit at a point of discontinuity. So again, all this is going to be given to you. Let f of x be equal to, it's piecewise, so x squared minus 9 over x minus 3 if x is not equal to 3, and 2 if x is equal to 3. Find the limit as x approaches 3 of f of x and prove it is discontinuous
Okay. I was like, oh.
at x equals 3. I don't understand why it does that.
I was like, are you writing
Invisible ink. I'm gonna let y'all get that before I. Alright, so the limit as x approaches 3 of x squared minus 9 over x minus 3. But if I went ahead and plugged 3 straight in, what's going to be the problem?
Would be undefined.
Undefined. 0 on the bottom. So I want to see if there's something I can factor. So the limit as x approaches 3 of, what does the top factor into?
X minus x plus 3 x minus 3. Whoa. It's a lag.
So then what happens?
You
You
can
can cancel out the x minus 3s.
Cancels. So the limit as x approaches 3 of x plus 3 would be what?
6.
6. But
What?
we're trying to prove that it's discontinuous. So according to what was given to us, at x is equal to 3, so f of 3 is equal to 2,
I forgot about that.
which is not equal to the limit as x approaches 3 of f of x. So it is discontinuous
Whoa.
at x equals 3. My iPad's updated and I don't
Yeah,
understand
was about
why.
to say, do you need, like, a new software update or
So
something?
since
Maybe it was the new software.
It's been doing that off and on for a while. I don't understand.
f of 3.
I wonder if like the pencil is starting to like go because I use it so much. So according to the problem, it said that at x is equal to 3, the problem was supposed to be equal to 2. But when we took the limit at 3, it gave us 6,
Gave us
meaning
6.
it's discontinuous.
Okay, so if it equaled 2, it would be continuous.
Mhm.
Okay.
All right, one more. This is a fast one. All right, so it's back to finding
Is it short?
one-sided. Yeah,
Okay.
I mean like 6 lines, but
Oh, that.
and two-sided limits. I feel like my writing is so bad because I can't see where it is. So we're given let f of x be equal to the int of x. Okay, that's a
Oh, there you go.
greatest integer function. Okay, or a step function. Okay, y'all remember what that parent function kind of looks like? Okay, it is, hold on. We're going to be finding. Basically, it's a graph that it does this. It's like closed on one side and then open. And it's like closed,
Oh,
Yes.
open. Okay, that's not exactly what it looks, but you get the point of what it's supposed to look like. That's not where the stuff is. But anyways, okay. So these are where the different sided limits can be a problem or can show that there's a problem because one side is open and one side is closed. So if I were to look at this, now it'd be easier if we had the graph in front of us, but I'll put the graph up in just a second. Hold on. These are back up. This is what would be given to you. It's asking you in 3 parts, but I'm going to write them all and then we'll solve them all at the same time. The limit as x approaches 3 from the left of int of x is equal to the limit as x approaches 3 from the right of int of x is equal to, and then we need the limit as x approaches 3 of int of x. Okay. So I'm just going to use the graph because it's in the book. So this is what this function looks like. Okay, so it's the step function. Now there's a step here, so on and so forth. So if we're looking from, we care about at x is equal to 3, so that's over here. So at x is equal to 3 from the left, okay, that's this value right here. Y is equal to what? 2. So that's equal to 2. Then from the right, that's this one. What's y equal to? 3. So, according to the stuff that we talked about at the very end yesterday in the notes, wherever it is, or not the very end. But if our left and right hand limits are not the same, then the entire limit does not exist.
Okay, so it doesn't.
So the answer to this one would be D and E for does not exist. Now, limits at infinity, we've done stuff with that before, so I'm not really going to do anything like at the moment with that. But that's just what happens as x gets really, really big or really, really small. But also, you could have a limit that when you plug the number in, you get like 1 over some giant number, which is like close to 0, or you could have some really giant number over some really, some other number, and it could go to infinity or negative infinity. So your answer could be it's going to infinity or negative infinity, or we could be taking the limit at infinity and seeing what's happening. So that'll make more sense when we see examples, but there's not really a good example before we get into the actual problems.
How did we get the 2 again?
Yeah, I did, yeah. So it's x as it equals to 3 on the left.
So
that means you start on the left and then go to where?
So as x is equal to 3, okay, so this is x is equal to 3. So from the left, so if we were coming from this direction, what is that getting close to? Because it's a straight across line, we're just pulling it from right here, which was 2. Okay. But then as x approaches 3 from the right, that means coming from this direction. And so it's a straight line. They won't always be straight lines.
Okay, I see.
Sometimes it's a function that may just have a hole in it.
Okay.
That point doesn't exist. It's like discontinuous, and that could cause it to be different. But I don't really know how in depth the book is going to get with that right now, but that's why it does that.
Okay, cool.
Yeah, it's like literally from the left and literally from the right.
Because
What's
at first
happening?
I was thinking, am I supposed to be